Okay, this C to point D. So from here, we have minus 7050x plus by 900x squared plus by 3000x. So 3000 multiplied by 1.5 is 4500 plus by m as a function of x is equal to 0. Let me 3000. Yep. Okay. So m as a function of x, or let's tidy things up first. Okay. So 7 minus 7050 plus by 3000 is equal to minus 4050x plus by 900x squared minus plus by, oh no, is that it? Minus by 4500. Okay, m as a function of x. Okay, so minus plus by 3000 minus 40. Okay, everything looks correct. So m as a function of x is equal to minus 9000 or minus 900x squared. Okay, then plus by 4050x. Yeah, I'm just bringing it over plus by 4500. Okay, let me see this again. Minus correct, positive correct, positive correct. Okay, so that is our equation number 2. Okay. Now, how do we know that this equation is correct? Okay. Okay, how do we know that this equation is correct? So, if we do dm by dx, okay, if we so when dm by dx is equal to 0, okay, x itself must be equal to 2.25 meters. Okay, so we have to prove this. Okay, we have to prove this, right? And you guys can visualize this mathematically. I believe you guys have done this in your math, yes or no, right? You guys have done this in your math before. So 2.2. So now we do dm by dx. Right? Why 2.25 meters? This 2.25 sounds familiar, right? It's exactly at the center, right, where fracture will occur. Okay, so when you differentiate, right? In fact, when you differentiate, you get your shear force, which we'll teach you later, or you guys have done this before. So dm by dx. So this is equal to minus 1800x plus by 4050. The whole thing is equal to 0. So therefore, x is equal to 4050 divided by 1800 is equal to 2.25 meters. So the equation is correct. Okay. So now we want to find the maximum bending moment. Okay. Now I'm doing this is because I know this is bending moment topic, but we are looking at bending moment equation is because you have to know the magnitude of the bending. Then you can solve for the bending moment. Then you can solve for the stresses, right? If you cannot find the location of the bending or maximum bending at all, okay, how are you going to solve it? Okay, so that's why I'm doing this. Okay, so from here, right, we know that mx will be equal to what? So we take the whole equation, minus 900 multiplied by 2.25 squared plus by 4050 multiplied by 2.25, then plus by, hold on, plus by 4500. Okay, 4500. So the maximum bending moment, so minus 900 times by 2.25 squared plus by 4050 times 2.25 plus by 4500. So I get 9056.25 Newton meter. Okay, let me do it again. Minus 900 times by 2.25 squared plus by 4050 times by 2.25 plus by 4500. 9056.25. So that is the maximum bending moment, as you can see, right? So there are two equations over here. Okay. Yeah, sorry. Yeah. So the other one is 8550. So how does the bending moment equation look like now? Okay. I know some of you could visualize this. Okay. And forming the equation gets the numbers. Okay. So I want you all to look at the two equation, and we can sketch this out using equation number 1, and then we can also use this by using equation number 2. Okay, so how does this actually look like? So we're going to sketch, okay, by looking at the parent function. So this is our x. Now I'm only going to focus on positive bending. Okay, I'm only, right, positive bending. Right, so this is 0. This is our moment. Why are we concentrating on positive bending? Because the magnitude we found is positive, and not just that. If you look at the deformation pattern, right? If you look at the deformation pattern, right? The deformation pattern is smiling face, okay? Is positive. Negative will be sad face deformation pattern. And if you look at the structure over here, the deformation is going to be what? Smiling face. Okay, that's why we are doing that. Okay, so from here, okay, the equation states that it is a negative slope. Okay, the x squared. Okay, so we have up to like 1.5, and then I'm only going to sketch until 2.25. Okay, and it's symmetry because the left is good to right. So it's going to do this. Okay, so when it reach here, this value over here is 8550, and then it's going to do the next one, and at this point it's also a curve. Let me be more distinct. It's a curve, and then it's another curve over here. Is equal to 9056.25 Newton meter. Okay, all right, so we're going to calculate. Okay, we're going to calculate like what this question asks at point C, and then we're going to calculate also at the max. Okay, we're going to calculate the stresses. Okay, after I calculate, we go for our first break. Okay, for 15 minutes. I know you guys had enough of my voice for like 1 hour 45 minutes. Okay, so we're going to find at point C. Before we can calculate at point C, we have to calculate IZZ. Right, so it's width, depth, cube divided by 12. Okay, so for this case, right, if you look at this diagram, so it's 80 by 300. Okay, so I'm going to sketch this over here. So this is 80 millimeters. This is our 300 millimeters. And if you draw our transformation, this is y, z, this is rotation about x. Okay, so we're going to find IZZ. Okay, so this is my ZZ. This is our ZZ axis. So parallel to the ZZ axis is our width. Perpendicular to our ZZ axis, this will be our what? Our depth. That's how you define it. Okay, not English. Okay, width is this, depth. No, it's on the axis that you are interested in. Okay, so the width about IZZ, this is 80. The depth is 300 cube divided by 12. Okay, so 80 times 300 power cube divided by 12 is equal to 180 times 10 to the power 6 millimeters 4, and this is equal to 180 times 10 to the power minus 6 meter 4. Let me do it again. 80 times 300 power 3 divided by 12. Yep. Okay. So you're going to find at point C, right, stress in the X at point C is equal. So we only, for this question, they only want us to calculate the maximum stress. Okay, they did not ask us maximum tensile or maximum compression. But based on the bending, you can see over here, if this is the moment vector, right, this will be equal. So this will be your compression. This will be your tensile. Okay, if you want to know, but this question did not ask for that. Okay, so we know that at point C, plus or minus the moment. So the moment we calculated is 8550 divided by 180 times 10 to the power minus 6. The y, right, is from the centroid, so it's equal to 0.15. Okay, so this will be equal to 8550 times 0.15 divided by 180 power minus 6 is equal to 7 point plus or minus 7.125 times 10 to the power 6 Pascal. Okay, let me do it again. 8550 times 0.15 divided by 180 power minus 6. Yep. Okay, so stress X max. Okay, so this will be plus or minus. So the maximum value that we found is what? 9056.25. So 9056.25 multiplied by, again, the same thing, divide by 180 times 10 to the power minus 6. So 9056.25 times 0.15 divided by 180 power minus 6. So this is equal to 7.54 plus or minus 7.547 times 10 to the power 6 Pascal. Okay, let me do it again. 7.15 divided by 180 power minus 6. Okay, 7.5. Okay. So anyone, any questions so far? Anyone? If not, what I propose is we go for 15 minutes break and then we're going to start at 9 o'clock. Okay, we're going to go for 15 minutes break. Thank you.